Good afternoon, ladies and gentlemen. Thank you for coming to the seminar. Following the last seminar in October, we have another distinguished tribology professors from the USA. Today we have our guest is Professor Komvopoulos. It's difficult to pronounce. It's a long name. But he's a professor in University of California, Berkeley. And let me just first introduce him to you. He graduated from National Technical University of Athens. Athens is in Greece, in 1979. And then he entered the Massachusetts Institute of Technology in Boston in 1979. And then he finished master courses in 1981 and finished in civil engineering. And he also finished aerospace and astronautics as well in 1981. And then he got a PhD in 1986. And then he moved to Champaign, Illinois, to become an associate professor, assistant professor in Illinois University in Champaign, where the Petros is working. And then he moved to Berkeley. Until then, he extended his research in tribology, not only tribology, but also in nanoscience. As you can read his autobiography, that his research is extends in many areas of the interfaces of mechanical and electrical engineering, surface physics, chemistry, and bioengineering. And yesterday he had another lecture on biotribology. So today I asked him to introduce tribology on the aspect of tribology that contribute to the energy consumption and environmental pollution. So please welcome Professor Komvopoulos.
Thank you, Professor Sujimura, for the introduction, and thank you all for coming to the seminar. It's a pleasure to be here to talk to you about part of some of our work and the work, of course, of others in that very important area that relates to environment and energy, and in particular the consumption of energy and the impact of some of those energy sources to the environment. I would like to make a few introductory comments about energy sources and impact to the environment before narrowing down my presentation to the topic of today's seminar, which is how, in particular, tribology is affecting environment and energy. So those of you that are not familiar with the term tribology, that is the science and technology of interacting surfaces. It is a term that is not very well known, although it's been around for a while. It was first coined by Peter Yost in Great Britain in 1966, who thought that it would be better to develop a term, to come up with a term that embraces three main disciplines that define this field, which is friction, wear, and lubrication. So those three words were used now to define the word tribology, which comes from the Greek word tribos, meaning rubbing, and logy, which is usually the end word for many fields of science and technology. So biology, sociology, they're all ending like that. So the definition is the technology and sciences that are behind the interaction of surfaces. And as we know in today's world that we have reached technologies that very much depend on interfaces, contact interfaces. spanning a wide range of conventional mechanical systems like bearings, gears, miniaturized devices like accelerometers in semiconductor industry, switches, RF switches, or even in the biological sector where we have implants, we have procedures that involve the insertion of needles or catheters. They all slide against some human tissue or arteries, and therefore we have an important role of these interfaces. In my two laboratories that you see here, we are focusing in some of these main sectors. And the example of my seminar today is coming from these areas, that is the energy sector, and in particularly how we can design more bio-friendly additives for synthetic lubricants. You understand that the lubrication of engines, auto engines and aerospace engines, is critical to the endurance and the reliability of these systems, and especially also as they become used more often, more frequently, and with the need of or lack of time for more frequent inspection, their reliability becomes even more important. And at the same time, energy resources are depleted, so the cost of running those engines increases. These two effects of high costs and impact of these energy resources, particularly fossil type of energy sources, creates two competing forces that are driving many economies and technologies to explore new alternatives in order to face these problems. And as I mentioned earlier, my goal today is to address, at least partially, those needs as they come from the tribology perspective. I will begin by first, of course, recognizing that there are many possible, even non-fossil type of energy sources, and people have recognized the need to explore many of those, including nuclear, solar, wind, biomass, hydroelectric, and geothermal, in an attempt to address future problems with depleting fossil resources, with the main difficulty in many of those examples of non-fossil technologies, the low efficiency, the conversion from mechanical, thermal, hydrodynamic, bio energy to electric energy is not as efficient as is from fossil resources. For example, in solar panels, the current efficiencies are typical of the 6 or 7%, when in an engine you can easily have 70 or 80% efficiency in converting to one energy type to another. But nevertheless, they're capturing an attention because they share some very common, except with the first one, feature. They do not impact as negatively the environment as the fossil resources. So returning to the fossil resources, it would be instructive to start first with recognizing some of these needs and demands as the years go by. And we can see here the demand by energy type and by fossil type. You can see a constant trend, a slope upwards, or even a sharper slope if we go by fuel type. And the most compelling conclusion that we can see from that is that oil and coal and gas are the main driving energy resources in the world. The demand is increasing as more countries are entering technological eras that require more energy resources, and the availability of such resources does not appear to increase proportionally, and we can have therefore this kind of total sharp increase in more recent years. This comes with an increasing penalty towards the environment that we live. we have seen many times oil spills that deplete the water and the water world that goes with that. We have also emissions from various plants that deplete the atmosphere and the air that we breathe. And we have even more significant global changes, like the so-called global warming effect, where you can see a gradual increase of temperature in our planet, with the implications affecting local microclimate conditions, such as in the North Pole, more melting of ice affecting the underwater world and also the other parts of our planet. In the case of health, which is an increasing concern in our days, due to these emissions, we have the depletion of the ozone layer, and then we have emissions that relate to microparticles or monoxides of carbon and nitrogen, lead, another important contaminant here, as well as particles, sulfur and sulfates and hydrogen sulfides that are all emitted during the combustion process, either from factories or plants or automotive applications or even in biomass. And many people are in the impression that technologies or resources that do not use fossils are going to be a solution to health and environmental problems, but they underestimate the process by which this can be converted to efficient energy resources. The process behind involves a lot of manufacturing, and this manufacturing can lead to emissions of this kind, and therefore this has to be actually counted into the equation. So the main air pollutants, we can classify them as primary and secondary pollutants. And in the primary category, of course, the first role is played by COx and NOx emissions. And of course, we have some others that are not into our control, that are volcanic eruption related. In the secondary pollutants are usually substances that are not emitted directly, but they are formed in the air by primary pollutants due to interactions that can take place. So these emissions here can lead to secondary products that occur in the atmosphere. And of course, we have the ground level ozone effect. That is one of the reasons that we have observed photochemical smog effects. Sources by air pollution is important to be recognized as anthropogenic first. These are the ones that the humans are mainly responsible. Human needs have created those. So we have the smoke stacks of power plants, manufacturing facilities. We have also mobile sources of pollutants such as vehicles and aircrafts that producing those. So these have come up with our needs of a different style of life and different comforts that require different technologies. And these technologies do not come free of any penalties. And these penalties are depleting our environment and consequently have impact to our health. Other anthropogenic sources are listed here. Of course, we have nuclear and toxic gases. The fertilizers that are used are also presenting some health problems, and some other daily used products that we underestimate their impact. They all contribute. In fact, I would add here in this list, I'm not sure it's included, air conditioning as one of the main means of depleting the ozone atmosphere. And one of the reasons is that the lubricant that is used for air conditioning contains fluorocarbons, that fluorine in this is released and is one of the main factors that depletes the ozone in the atmosphere. And we have also some natural sources here that are adding to the list of the sources for air pollution. So here we can see air pollution emissions. As people become aware of these problems, you can see a trend to minimize the total emissions as well as main emissions of this kind. But nevertheless, this trend is not as steep a slope as we would like to be, especially as the statistics of various health problems increase, as we started collecting them since the 80s, and recognizing the importance of even these levels of pollutants to be still very high for our health. And if we want to look at this by sector, source category, we can see that the main category here is highway vehicles that are constituting a major part, and also off-highway vehicles and other miscellaneous sources as well as production manufacturing plants. So these four are the main sectors from where the largest level of these pollutions and impact to the environment is coming, and of course they are drawing the most of the attention here. And if we look at the pollutants associated with emissions, then as expected, we see CO and NOx being the main contributors. So having reached that point, then it is clear that if one needs to begin to address this problem, he or she will have to draw attention first to the biggest slice of this pie, or the previous pie, which is air pollution, and especially associated with automotive, either highway or non-highway vehicles, and manufacturing plants that produce emissions that contribute directly or indirectly to CO and NOx. So my talk today is going to focus into these products that are a result of from the automotive sector. But before I do that, let me add that the increase of these emissions of CO and NOx in terms of some quantitative numbers that add up to these percentages are an indirect effect of the presence of some elements like phosphorus and sulfur, which are main ingredients in additives used in synthetic oils for gear oils or engine oils to maintain their efficiency and optimum combustion process by reducing friction and wear between the various interfaces of these mechanical systems. But these additives that they are effective in lubricating those components of vehicles contain phosphorus and sulfur, which turn to be poisoners of the catalytic converter. So they tend to gradually poison the catalytic converter, causing emissions of CO and NOx to be produced more readily, released to the atmosphere. As a matter of fact, this upsets the optimum operation of the car, because there are sensors in the car that even sense that something is going wrong, the emissions are exceeding a certain level, and the consumption of fuel is affected by this optimum now shifting away from the real optimum that the car has been designed for. The result is that during the poisoning of the catalytic converter, not only we begin to create more emissions, but also the efficiency of the car and the consumption of fuel increases. So one of the challenges that I will try to address here is, what if we try to do a gradual step towards the right direction, which appears to be huge for the oil industry, is to reduce some of these important elements that have made some of these additives for more than 40 or 50 years to be the prime additives that this industry is using. In particular, phosphorus, to reduce it by about half in terms of its content. You may be surprised that these numbers are very small, but additives represent a very, very small fraction of the content of oils, but nevertheless their effect is much far-reaching. And so here you can see the attempt to reduce the presence of sulfur in the gasoline, to clean better the sulfur gasoline, with the years approaching levels that now are tighter, and here is where the levels of regulation, the present regulations exist. So let's focus in the theme here is how can we reduce air pollution contributed by highway vehicles in particular, and what would be possible scenarios that one can immediately begin to identify. Well, one would be to reduce highway vehicle usage, and this appears to be going in exactly the opposite direction. More vehicles are appearing on the highway, especially as they become more, people become easier to buy those. And also because public transportation in many parts of this world is not as efficient as it has to be, so that the use of vehicles can be avoided. Another possibility, of course, that seems to be more plausible is to reduce the causes of the problem. So as in the medical field, you have to identify the cause of the disease and in order to cure the disease. And this, as we have seen already, appears to be these ingredients that these elements have, these additives have, which is phosphorus and sulfur. The most common additive that is used by the automotive industry is zinc dialkyl dithiophosphate, a name longer than my last name, which has, fortunately in this case, an acronym, ZDDP, while I don't have an acronym. So we will refer from this on as ZDDP. This is a long chain molecule that contains phosphorus, zinc, and sulfur, and it's incorporated in the synthetic oils. And today we will learn what its main role is in protecting engine parts and by reducing friction, therefore improving the efficiency of the engine, and improving the wear resistance by forming protective tribofilms. I start up front referring to them as tribofilms because they are forming by the rubbing process. Tribo, you see the tribology we said before, and it's therefore a chemistry that is not an equilibrium chemistry. It involves rubbing between the surfaces. The rubbing process activates those surfaces, causing these molecules that are incorporated into the synthetic oils in these additives to break up, react locally with the surfaces, and forming these so-called tribofilms to protect those surfaces. So the pros and cons that come with these additives is that they reduce catalytic and converter poisoning, increase lifetime efficiency, reduce CO and NOx emissions, and reduce the SO emission. So if we reduce them, we can accomplish many of these things that seem to be pointing in the right direction to minimize emissions and improve our environment. But the cons is that we will probably reduce the wear protection. These are referred to as also anti-wear additives. And we will reduce the life of the engines, the reliability of the engines, and so forth. So how can we gain all of this while we can lose all of these things? Obviously, that requires innovation. And that is one message also I want to send to the students is that always try to think out of the box. This is a term that we often coin in US, thinking that, indicating that do not always follow the conventional wisdom or the learned approach, because you can only do incremental changes. Sometimes to revolutionize a field, a direction, you need to think out of the box differently. And in cases like this, you have to think also out of the box, and instead of trying to reduce only the content of these and worrying about these problems, be innovative and think of what other elements that are not depleting the environment can be used instead of these phosphorus and sulfur elements. So how can we reduce the content while we maintain low friction and low wear, better wear protection? Okay, so let me summarize this first part by indicating the impact of tribology, therefore, in the automotive engineering. And because this is a busy slide, I will try to focus into the italicized words. We're looking at lubricant formulations that will achieve better protection for automotive components like gears and bearings. This can be accomplished by formulated synthetic oils. These oils will produce these wear-resistant tribofilms that will protect our surfaces, but we want to make them without additives that can be hazardous for the environment. They have, therefore, these additives at the temperatures that we'll encounter to react to form these protective films that will lead still to the formation of durable tribofilms without containing these phosphorus and sulfur additives. And so an example that you will see me presenting today is to use boron instead of phosphorus. We've seen earlier that reducing by half the content of phosphorus is a major step towards that direction. Let me give you a very quick reasoning of why we use phosphorus and sulfur and what the role they play, which will become more obvious later. Sulfur forms sulfides and sulfates, which are easily shearable phases. If we have those in the tribofilm, we'll produce low friction. Phosphorus forms hard, glassy phases, which provide the wear protection on the tribofilm. So the tribofilm is a mixture of a biphasic material made out of soft and hard phases that synergistically provide the low friction and wear resistance. But because of the softer phase, it's going to wear out, and that's why it is referred to as sacrificial film. The role of the additives is to immediately intervene and reform it everywhere on the metal surface that has been removed. So you understand that there is a continuous affinity of the surface for these additives that are broken up and activated by the rubbing process to strongly adsorb on the exposed metal surfaces every time that the tribofilm locally is removed. It's worn off. So that process, therefore, leads to a continuous reformation of the tribofilm, and that's why it is referred to as sacrificial film, because it sacrifices itself for the sake of protecting the precious engine metal underneath. Okay, so why would surfaces wear out? We ask the question. And why is energy dissipated when we bring two surfaces in contact and begin to slide one relative to the other? Well, if we look into with the right eye on these interfaces, we will observe that although macroscopically these surfaces have been phased and polished and smoothened, and they're very well maintained in terms of the tolerances, at the microscopic scale they still have some roughness. And regardless of how much you press those two surfaces against each other, they will never become 100% in full contact or full mating with each other, but they will continue to interact at the higher peaks of these protrusions, which from now on I will refer to as asperities. So asperities on each surface come to interact with the asperities of the other surface. And so if we had made a calculation of the pressure that we can transmit through this seal based on its apparent area and the thrust load that we are applying, we will be surprised to find wear of this seal despite that this pressure being very low, because actually the pressure that the seal sees is much higher due to these stress razor points, the asperities. You can think of the load as being parallel lines of stress, constant stress. This is the nominal stress that you calculate by dividing the load by the apparent area. And this stress you can think as current lines that are coming to pass from one surface to the other. There is a vacuum here, a void, and they cannot pass obviously through that because it's a high dielectric material, so they will have to detour and pass from here. This detouring causes a lot of traffic jam here, which in more scientific terms represents stress concentration or stress gradients. High stresses therefore arise because the stress that was going to pass from here, the stress lines all pass from the same point. So the local material will see 3 times, 4 times, even maybe 10 times higher local pressures than what we think the material is experiencing. If we add also a tangential force when we start sliding, you can see how easy it is to begin to wear out this material, and the process starts at these microscopic asperities where the two surfaces wear out. Then, of course, the gap will increase, and we have leakage into that seal, or we have vibrations into the bearing surface that has been roughened as these asperities are removed. But is this happening all the time in every system? In an engine, for example, where we have a piston that is reciprocating in order to induce the combustion process. Does the piston rig, which is preventing the rig from touching, all of the ring touching the inner wall of the cylinder, really interacting continuously with the wall, or only at certain instances of a given stroke cycle? Well, we can understand this by looking into the fundamental definitions of the different mechanisms that describe surface interaction, known as those represented by the so-called Stribeck curve. The Stribeck curve was obviously a curve that was introduced by Dr. Stribeck in the early years of the previous century, an engineer of SKF, the most well-known in the world, I guess, bearing industry at the Netherlands. And he used a plot of the friction coefficient and this ratio of the viscosity times the speed divided by the load to represent the various interaction regimes that two surfaces in relative movement can undergo. So when this ratio is high, means that you have either a very viscous material separating the two surfaces here. That could be a wax, a high viscosity grease. That means that the two surfaces do not get to interact like we saw here directly, because it's very difficult for this high viscosity material to be squeezed out. But if the viscosity is reduced because of a temperature increase, we know that the viscosity will decrease. We can find that this will be squeezed out so that this term will begin to decrease. This can also happen if the speed is decreased. So when will the piston reach the upper end of the cylinder wall and temporarily will stop to reverse? At that instant, the speed is 0. We can also see that in the case of a bad design, that we have designed and made a mistake, we have overloaded the bearings. We use fewer bearings in our bearing assembly than what we should have. That can result into a larger load per bearing. That again will have a similar effect. So when this ratio assumes relatively high values, the two surfaces are separated by a sufficiently thick fluid film, sufficient thick so that they don't either interact with each other, they don't see each other, and that is referred to as hydrodynamic lubrication. So we have hydroplaning between these two surfaces, and the load is transmitted from one surface to the other through the pressure that is arising into this pressurized film. As this ratio decreases, the friction coefficient begins to decrease increase slightly. I should point out that this is a log scale. So from these values that are in the order of 10 to the minus 3, 10 to the minus 4, we go to 10 to the minus 4 values. And this is referred to elasto-hydrodynamic lubrication. Now the film between the two surfaces is thinner because this ratio has decreased. So it undergoes a higher pressure, which pressure now begins to deform those asperities that, although it may not be in direct contact yet, they see a high pressure and they undergo elastic deformation. And so elasto comes from the fact that the surfaces cannot be treated as rigid as here, but here they're elastically deforming. Still, though, it's a hydrodynamic film, and you can experience lower friction than here because the thickness or the volume of the sheared material has been reduced from here to here. Also, the shear rate has been reduced because now I'm moving slower. So both of these effects will explain why there is a slight trend in the friction coefficient. Things become getting bad after this point, where we can see a sharp increase in the friction coefficient. And here we can see values that are 3 or 4 orders of magnitude higher than what we had in the previous regimes. This is because now we have squeezed out all this fluid. This green fluid that you see here has been completely squeezed out between these two surfaces. And we have a case like this. And if we are not having an additive that will form this tribofilm between these two surfaces, as this orange layer here, in a case like that, we will have strong tendency for the two surfaces to wear and adhere with each other. That is the reason why the friction coefficient increases, and that is the reason why we need the so-called extreme pressure lubricants, that they will operate in these high pressures due to the surfaces being so close, to form these protective films, such as the one that is shown here by the adsorption of a hydrocarbon on an iron surface that actually has an oxide, since it's not a noble metal. And this adsorption can happen through a iron-oxygen bonding with this molecule to form this close-packed configuration of a monolayer that will play the role of this orange tribofilm. And as we will see, that might not be sufficient. We will need to have a solid film that will form, such as an iron sulfide, iron and sulfur, or an iron phosphate. And that's why, because this is a hard glass surface. So we said that zinc dialkyl dithiophosphate is one of the prime additive in the oil, but unfortunately this has sulfur and phosphorus. And although this is the anti-wear additive to oil, and we have more than 30 million pounds only in the US sold per year, it's the major contributor to tailpipe emissions. So the sulfur is temporarily poisonous, the catalytic converter, and the phosphorus coats and deactivates the catalytic converter. That reduces its ability to reduce tailpipe emissions and also upsets the optimum combustion cycle of the engine, causing further implications. So let me start first by seeing what we can do to address this problem for gear oils, and in the later part of my talk I will refer to also to synthetic engine oils. Let's look at a gear lubricant. A base gear lubricant, referred to as base gear oil, usually contains very, very small amounts of sulfur traces, that to a point that if it was to use by itself, it would not be a problem for the environment. Here we have also white oil as a control sample. This is the most inert oil that you can have. It's basically a rich in naphthenic hydrocarbons oil that does not react with the surfaces. Only the molecules will tend to attach to the surface. Blends 1, 2, and 3 are the base oil on which we incorporate a new material, a boron, with reduced levels of phosphorus, compared to the zinc dialkyl dithiophosphate. So this represents contents of zinc dialkyl dithiophosphate. You can see much higher sulfur and much higher phosphorus here. So here we reducing the phosphorus to this level or this level. From weight percent, I'm going to parts per million, reduction in phosphorus, reduction in sulfur also, by adding another element that is not producing environmental effects, boron. Now, how did I pick boron? I picked boron by thinking out of the box. That is saying that, well, I need protection. If I remove the phosphorus, which is the main ingredient that makes this film to be wear resistant, this film will not last very long and may not provide the protection. So I need some other element that can do a similar job. What job is the phosphorus doing? Is forming a hard glassy phase. Well, boron can form a hard borate phase. And in fact, this has been used also to form other elements of boron, like boron nitride and boron carbide, to use them as a coating material. So we will be looking throughout what I present here on bearing steels, standard bearing steels. We are not going to bother with tweaking the chemistry of the steels that are typical 50 to 100 bolts sliding against a disc in the presence of these different oils. So let's take first a look and see what typical features we can see at low temperatures and high temperatures. You can think of this as the engine being relatively cold when you start the car, and this could be a hot, maybe more than the typical high temperature, so it's sort of an upper bound, worst scenario case of the temperature of the engine after steady state. So we can see that the white oil, the gear oil, and then the blends 1, 2, and 3, that they exhibit very different wear characteristics. This one is severely adhesive, worn by adhesive wear. You can see a lot of craters and material removed. This one has undergone excessive abrasion. That's because the oxide particles of the metal surface, in this case iron, as soon as they remove, they begin to abrade the surface. But the blend 1, 2, and 3 appear to be producing a better situation. In fact, blend 1 appears to be forming a film, but this film seems to be brittle and is cracking. No surprise, we have boron and very little sulfur in this film. And in these cases, we have reduced phosphorus and boron, but more sulfur, so these are softer films, so they undergo more abrasion. Things become different when we go to the higher temperatures, that the reactivity is increased, and we can see that this film now that is forming is not as brittle as at the low temperature, and so the brittle film now is forming with these conditions. This is the high phosphorus and boron content. So at the high temperatures, which is mainly where we need to have the protection, these two blends appear to be forming a film that prevents this excessive damage of the metal surfaces and it doesn't have such a high phosphorus or sulfur contents. If we want to put this in a more comparative way in terms of reduction in friction and wear, we can see here what the different blends have done, and focus in blend 2, which I have highlighted here as the one that is producing the best performance, especially at high temperatures. So at room temperatures, we can see a tendency for friction to decrease, but I will not call this a significant effect. They are about 0.07, considering the standard deviations, no significant effect. It is significant at the high in terms of the wear rate at the room temperature, and especially significant at the high temperature. You can see that the two oils without these three additives here will be impossible to use in any automotive application due to the almost fourfold higher wear rates. At the higher temperature, we should recall that the chemical reactivity increases. The actual temperature could be much higher because of the rubbing process. When the surfaces slide at their asperities, the local temperature is much higher due to frictional heating. And so the actual temperature is not just 100 or 120 degrees, but could be much higher during the sliding process. And that is a critical factor to induce these reactions between those additives to form the tribofilm. So the tribofilm forms, and this is the one that produces the lowest wear, as you can see, and that is the blend 2. So in this blend, we were able to reduce the amount of phosphorus from 0.11 weight percent to just 428 ppm. We have even reduced almost by 30% the sulfur, going to 1%, by simply including boron. So the boron has done the job actually much better than the phosphorus and sulfur. The green is the competitor, the ZDDP, the currently used additive. We can see that the blend 2 is performing even better. But here I have not shown you how the film is forming and when is it forming. So again, thinking out of the box, when we have a wear tester like that, where we have a spindle and the bearing, you can see here the bearing eccentrically mounted so that it spins around. And here is a container inside which the disc is sitting. Here is the disc, and here is the ball. So this is rotating. We have a heating band around here, so we can raise the temperature in this container inside which we have the oil with the additives. This is a difficult experiment in every sliding case. It's a difficult experiment, I should admit, because it's a field where you don't actually see your specimens. In pretty much 90% of the fields of engineering or biotechnology, we can see our specimen or the surface of the specimen. Here we're dealing with interfaces, sliding interfaces, which are hindered interfaces. So we need to develop in situ methods to determine what goes on into these interfaces as they slide. So what we did here, something quite simple, is to make these two samples part of an electric circuit that enables us to measure the contact resistance or the contact voltage that is exerted at that interface by using this very simple circuit. So clearly, if I have a 0 contact voltage measured during the test, that means there is no resistance in that interface, and that means one of the two or both of the two following things. Either there is no an insulating film forming, so no tribofilm formation, or if there is a tribofilm that is forming, then it is semi-conductive or conductive. Usually sulfates are conductive. Phosphate phase is insulating. Borate is also insulating. So if the film contains phosphates or borates, it should give me a high contact voltage, and it will give me an increase of this contact voltage when the film begins to form. If it doesn't contain any of these, and I have incorporated those in the film as additives, that means that the reaction did not occur and the tribofilm did not form. Or it was removed much faster than it was trying to form by the wear process. So let's take a look at what happens to the same. I took out the mineral oil now, so now we have only the base oil, and then the base oil with these different formulations. Remember, the second was the one that we saw was the best performing. So if we look at the coefficient of friction and the contact voltage for the base oil that has very little sulfur, we see high friction and fluctuating friction, 0 contact voltage. You may ask about the iron oxide, whether it's an insulator and should have produced a contact voltage. This is, first of all, very thin and very fragile. And if it's something very thin, you can still have tunneling through that, so you will get zero resistance. Or more importantly, if it's fragile, it's removed, and therefore you have no voltage. Now in the case of the blend 1, we can see that we have an incubation period, some activity is happening, the voltage fluctuates, and after sliding for some time, we have a sharp rise and establishment of a high contact voltage at steady state. At the same time, the friction begins to drop. In the case of the second blend, we see that this is more unstable than that, but it starts to form earlier. We can see these sharp spikes and fluctuations of the contact voltage that is no longer zero, reaching a steady state that is more fluctuating than this, but overall producing better wear characteristics. These fluctuations may indicate that it's rapidly removed and is reforming, as opposed to this one being mostly formed and very slowly removed, but this one may have better wear characteristics and friction characteristics because of its different composition. So with this contact voltage, we can determine the formation of the tribofilm and how long does it take. This one takes less because it starts sooner than this, which is important because it's indicating the reactivity, the chemical reactivity we have between the surfaces and these additives. So to further understand this tribofilm formation, we can say that the friction coefficient or the contact voltage has an incubation period where the surfaces become activated. When you have rubbing, the two surfaces will be electrified. You will have charges that are building up there. The formation of these charges can contribute to catalysis when the molecules of these additives break apart and you have charges there. This can contribute to reaction. So that takes place in this range. So when we reach a critical stage of activation, we have the chemical reactions taking place and the film is forming and reaching a steady state or slightly dropping, but reaching a steady state that is non-zero. And so we can see here that the sliding distance for these three blends increases, but the most important is the wear coefficient for the base oil and the two blends at these two temperatures, how much has been reduced by these additions of boron and reduced sulfur. So here we're going to think again out of the box and say, okay, people have been using metal deactivators to stabilize the fluids from becoming deactivated by metal ions. And they have never bothered to think of whether this can also provide, at least partially, the same work that these phosphorus and sulfur containing additives can do. So what if we study if they have any effect? And we can do that here by looking at the blend 1 that has a sulfur containing additive and the base oil. So this, the second one will have a phosphorus containing additive and the base oil. So these are what we're trying to change. And we can change them by looking at an oil that has just the metal deactivator, which is metal oxide complexes, and the base oil. So it doesn't have any phosphorus and sulfur, or has some of that and some reduced amounts of the other two. And again, using the same method, we can identify the formation of these tribofilms. So in the base oil, we see the same thing, high friction in both low and high temperature, zero contact voltage. In the cases of blends 1, 3, and 4, we don't see the formation of a film. Remember, I have repeated here the formulation so that you can see what we are talking about. 1, 3, and 4 contain sulfur. This, and this contains sulfur. And this one does not contain any phosphorus or sulfur, so it's just the metal on itself. So they are all either metallic or semi-metallic, and that's why the contact voltage does not increase. But it doesn't mean that the film is not forming, as it is indicated at the high temperature by the sharp drop of the friction coefficient. So we can see here that the film formation is not captured in situ, but it is happening as the friction decrease takes place. But blend 2, which has phosphorus here, that's the blend 2, we can see that begins to form the film and rapidly fluctuates. This means an unstable film at temperatures that are not enough to induce rapid reactions so that the film can rapidly form. But if we go to 100 degrees C, we can see that the film, as soon as it forms, stabilizes, and it's always forming much faster than it is worn off. So if we take these chemistries with the metal deactivator and we compare them, we can find again that these blends that have reduced phosphorus and sulfur content now having the metal deactivator here and here actually behaving equally or even better in terms of the competitor, which is the last one that contains the full phosphorus and sulfur and very small amounts of the activator. So you can see 2 and 3 here, especially at the high temperature, which is the shaded one. The blend 2 has the lowest wear compared to the other cases. So again, we have replaced one of the elements that we want to remove from these additives to improve emissions. And this gives us some further idea of the formation of these films. Again, recognizing that once we change the chemistry, the reactions that take place with the sliding metal surfaces can cause different wear mechanisms to take place. Often in industry, they tend to say whether we have mild, medium, or severe wear, and that is not really revealing how to solve the problem. You need to know the mechanism. What kind of wear mechanisms? There are various types by which material is removed, various wear mechanisms, such as abrasion, adhesion, delamination, plastic flow, and you can see the morphologies that we have here when these films are forming or not forming, what is happening. For example, here we can see a film that has formed and actually has confined rubbing only at its higher peaks. These are the highest islands. You can see the rubbing process that has changed their color, but is protecting the surface, as opposed to this film that is too brittle. The formulation that was used here was producing a brittle film that is breaking off, but if this exposed metal rapidly reacts with the additives to reform it, as happened here, then that can be also a possible solution that we can accept. I will skip the chemistry. This is XPS that shows the composition of the films in order to go to the summary of this. So what we can say about these gear oils, that the first blend that had the base oil and the sulfur-containing additives had a Tribofilm formation that was sulfide but was not protective. The second blend that has the phosphorus additive, it formed a film that was mainly brittle, was containing phosphates. And the blend 3 that had the metal deactivator had the Tribofilm that contained nitrogen and sulfur. This is what the chemical analysis showed, which are typical constituents of the metal deactivators. This was performing better than that, and even better than that, which is the phosphorus and sulfur containing oil. How are we doing with time? I have to speed up. So let me skip this and go to the engine oils. So in addition to gear oils, we have engine oils, and here the specs are different. So we have to worry about these as well. How do we lubricate the engine? And here we will see that we can use molybdenum to replace the phosphorus and sulfur in ZDDP, the so-called molybdenum complexes. Molybdenum, again, can form a hard phase and therefore can take the role of at least phosphorus, reducing the amount of phosphorus, if not eliminating the phosphorus. So we'll see here the comparison of 7 different types of formulations. 1 that has no additives, there's a base oil. 2, 3, and 4 that have the base oil, but something that we refer to as molybdenum additives. And then 5, 6, and 7 would be containing some of these ZDDP. We refer to the secondary and primary ZDP and the molybdenum complexes so that we can see whether synergistic effects take place. So this is a busy slide, of course, but it's comparing base oil blend 1, 2, 3, 4, 5, 6, 7, and so forth. I'm drawing your attention here that the film is forming as the contact voltage indicates. That's a phosphate film. And here as well, this is the blend that has the ZDDP and molybdenum, so we can form hard faces that are glassy in nature because of the presence of phosphorus and zinc, and soft faces like molybdenum disulfide because of the molybdenum contents that is known to be a solid film that lubricates the surfaces. So it's better to look at the comparison here, and we can see that the different oils ranked on the basis of friction and wear rate, and we can see that the blend 5, which contained a reduced amount of phosphorus and sulfur because of the molybdenum complex 1 additive, it produced the lowest friction and the lowest wear rate. So another example of replacing a significant amount of phosphorus and reducing the friction and wear. And again, similar information we can extract from these pictures as far as the wear mechanism. So the combination of ZDDP and type 1 molybdenum compound produced the lowest steady-state coefficient of friction of about 0.05. This is very low friction for the boundary lubrication regime. And also the incorporation of ZDDP into the base oil generally enhanced the wear performance, but we know that this is not what we want to see. We want to replace this. And this was accomplished by including these molybdenum-containing oils that improve significantly the wear resistance by replacing the phosphorus and sulfur elements that are present by the ZDDP. And the last example of, again, non-conventional thinking is to think about the role of detergents. Detergents are also incorporated in synthetic oils. They are, as the name indicates, they tend to clean the engine from undesirable compounds, but no one has ever thought whether they can replace, at least partially, some of the additives. So here we looked into the effect of these detergents. You can see different detergents here that are incorporated with the ZDDP, with reduced levels of ZDDP. And what you can see here is that if we plot the wear rate as a function of load applied to these wearing surfaces, you can see that initially we have no wear or positive wear. Positive wear will indicate that the tribofilm is forming faster than it is removed. So something is deposited on the surface. So instead of having loss of material, you have extra material. And there is a transition to negative wear, that is loss of material, that is affected by these different blends. And we can see that the blend 3 has the higher load carrying capacity. It has to go even at 6 or 7 kilograms before it starts producing wear. Any loads below that will not cause the material to wear out. And so we can see here, therefore, that the effect of these additions can be included into the wear resistance. And the characteristics we can see here at the low temperature and high temperature again indicate the formation of this in blend 3 and blend 1. You can see that these white spots indicate the formation of a film. The darker spots indicate where the film has been worn off, because just before we stopped the test, that sliding took place there. But this film continues to form. So in the next cycle, if we had the picture, you will find that these dark regions appear bright, and the bright regions here appear dark because these are higher and they will wear out in the next sliding cycle. So let me summarize here that the addition of ZDP and the thickness of the tribofilms that we have seen here was affected by the presence of these ingredients, and blending with these detergents, especially with the one that contains sulfonates or over-based phenate detergents, resulted in more wear-resistant films containing boron and primarily boron. So this is the order by which these detergents, the detergents are in the parentheses here. This was the number 3, number 1, and number 2. The base oil has the lowest wear resistance, and then the next was higher, was blend 3. Blend 2 was the best. So let me finish by emphasizing what we discuss here and what we learned today, that we have all recognized that there is a lot of growing demands for consumption of energy that have led to almost tripling the consumption in the last few years. The majority of the energy that is spent comes from the fossil fuels. It's almost 70%. And although there are non-fossil technologies developing, the conversion efficiency there is very low for replacing fossil energy resources. So there is a strong interest to develop efficient and clean and renewable energies, such as wind and solar energy. We talked about environmental problems that have increased the severity in recent years, and the seek of solutions that relate to the development, optimization, and implementation of more environmentally friendly tribological practices, such as those that we saw in this seminar, in particular the formulation of better for the environment additives. The term green, of course, is a term that appears in any manufacturing or technology sector that targets improvements of the environment. So green tribology for ecological balance is important to begin to develop. There is, I should say, a lot of disposals that are used for tribological applications, such as the semiconductor industry uses a lot of chemicals to do CMP, chemomechanical polishing of wafers. And these chemicals are, again, not appropriate for the environment. They are dumped into the landfill. So we need to minimize waste and extent of equipment life by using more innovative approaches, increase sustainability and protect human health, and develop more resources using green materials, and finally rethink and change the standard practice and polluting technology responsible for these emissions and the negative impact that they have in the environment. Thank you very much for your attention.